switch off their cameras when it gets going, just to keep the bandwidth going, and then we can have Q&A at the end.
Great. Cool. Thanks, Rob. Are we recording? Oh, yeah, there it is.
Yes.
Right. So, hi, everybody. So, thanks for joining us today for another iBind seminar. So today we'll have Feng Wang from China, who has until recently been or who was a PhD student at the University of Quebec, and so basically, I think in his PhD work, a lot of the work has focused on utilizing and working with blue intensity, and so Feng's published a couple of papers in relation to this. And I think just today in general, he'll be presenting some of his work from his PhD, specifically maybe with a bit of a focus on some methodological innovations to sort of address some of these staining issues, specifically in relation to subfossil lake material. So I think that will mostly be what he'll be talking about today, and then also some other ongoing work in Canada. So whenever you're ready, Feng, take it away. Oh, did we lose him?
Have we lost him?
Yeah, hold on.
I'll email him.
Everything was fine until now.
Yeah.
There we go.
Okay,
right.
so I thought I was disconnected, but it's all right now.
Still here.
Okay.
Okay. So I'd like to know if I can start my presentation.
Yeah. Yes, please.
Okay, okay.
Go ahead whenever you're ready.
Okay. Small. You see my slides? Okay, so hello everybody, Happy New Year, I'm Feng. I feel good honor to be invited by Dr. Milos Rediba to give the first talk of 2022 to the iBind community. Last November, I just completed my PhD in the University of Quebec at Rimouski, and I'm now doing my postdoctoral research in the Institut National de la Recherche Scientifique, Institute of Scientific Research in Quebec City. And today I would like to share with you a part of my PhD study related to the blue intensity method and my perspectives on the BI method. And my topic is challenge of the blue intensity method in presence of lake subfossils. Although I think most of you are quite familiar with blue intensity, I would still like to begin with some basic introduction to dendrochronology and blue intensity method. Tree rings are very important nature archives that have very wide applications in different research fields. Paleoclimatologists use tree rings to reconstruct annually resolved climate variabilities over centuries to millennia in order to better understand the recent climate change in historical contexts. Ecologists consider tree rings as very important indicators of ecological disturbances in the past. For instance, the forest fire scars on the wood could be used to indicate the occurrence of forest fires, and some unique growth patterns related to disturbances such as epidemics could be used to infer the insect outbreaks in the past. Archaeologists are also very interested in tree rings because tree rings may serve as a very important dating tool for the wooden artifacts. I think for sure tree rings have much wider applications than what I've introduced here, but I think a lot of us study tree rings due to its significance in paleoclimatology. Now let's look at the 2000-year temperature reconstruction developed by Page's 2019, which has been widely cited. This reconstruction is in fact a multi-proxy reconstruction based on different types of proxy data, such as corals, sediments, ice cores, sponges, and tree rings. If we look at the site map and the figure in the bottom, we could see that tree rings consist more than half of the network, both in space and in time. So why tree rings are so important? This is because tree rings have very wide spatial coverage, and also they have absolute annual resolution. In fact, tree rings themselves cannot be used to reconstruct climate, but multiple tree ring metrics can do. For instance, the ring width, density, and stable isotope data measured not only from the entire tree rings, but also the early wood and late wood part of tree rings are very useful. Among these metrics, I think the total ring width, or we often say ring width, and maximum late wood density, sometimes we also say maximum density, are most commonly used in climate reconstructions. Many papers have already shown that MXD is superior to ring width in terms of retaining climate signals. The figure on the left shows the correlations with spring to summer temperatures for density in blue and for ring width in green. We can see that in average, the temperature correlation is around 0.75 for dense data, which means that around 50% temperature variance could be explained by density. In contrast, ring width data could only show explain for around 25% of temperature variance due to a much lower correlation with temperatures. In addition, MXD data is also less strongly affected by biologic memory, so it could better capture abrupt climate changes such as volcanic cooling. The figure on the right shows that ring width data, which are in green, have attenuated responses to volcanic eruptions compared to dense data. If we search for the two types of proxy records using the NOAA International Tree Data Bank, we could find more than 5,000 ring width series. In contrast, there are less than 600 MX data ever developed. Even so, I think MX data are highly demanded in practical large-scale temperature reconstructions. For instance, in the famous entrant reconstruction, more than half of the data points are related to density or density composites, which are indicated in green and purple colors. So that means we are aware that we are in great need of dense data, but why dense data are much less frequently developed? The most important reason is related to the methodology. In general, the dense data are measured using X-ray radiography, or we say X-ray densitometry. When we measure the samples, we have to slice them into very thin pieces and place them on film. X-ray will pass through the object, and finally we will obtain a film like this on the right, where tree rings are showing gray colors. So we can then use a calibration wedge to convert these gray values into wood density. This method is, however, quite expensive. For instance, the wedge system is one of the most famous systems designed to measure tree ring density. However, very few laboratories could afford it. In addition, the X-ray densitometry is known as a kind of time-consuming method due to its complicated sample processing procedure. So around 20 years ago, a new and cheap method called blue density was developed in order to provide surrogates for X-ray density data. Unlike densitometry, the blue density only relies on flatted bed scanners, and also it only measures the light reflectance of tree rings on the blue channel. But please note here I give a very bad example for blue density measurement, because in general, we will need to put a black box to cover the scanner in order to avoid the influence of external light. So in the very early studies, they used blue light reflectance to compare with density data. This parameter, however, is negatively correlated to the X-ray density. So in order to make these two parameters comparable, we generally have to invert the blue light reflectance. And one option is to use the equation here. So the inverted values are widely known as blue density data we are using today. In fact, the blue density method is quite promising because a couple of papers have already shown that the late wood blue density is quite similar to X-ray based MXD measurement for a number of tree species such as Scots pine and Norway spruce. One may be quite curious why we only use blue intensity rather than the red and green intensity. This is because the very pioneer study of Mike Carroll 2002 have shown that the blue intensity data showed highest correlations with the X-ray density. To explain this, the authors assume that the blue reflectance and X-ray density are all related to the amount of lignin content in cell wall, because they found a paper showing that the two parameters similarly respond to late summer temperatures. This assumption has been repeated for many years, but if we look into this paper, we could find that the time series of lignin content and MXD are not significantly correlated with each other. So I think this lignin content assumption might not be valid. Until 2020, Jesper's work have shown that the cell wall composition is irrelevant for the temperature signal of little density and blue intense data. And they found these two parameters are directly related to the anatomic density, which means that all the little density and blue intense data measure the wood structure. But as a wood scientist in the past, I believe that blue intensity is still better than red or green intensity because blue light reflectance is less likely biased by non-structural variations, because some substances such as resins and tannins reflect more red and green lights. In recent years, there is a growing number of blue intensity publications, in particular since 2014. I tried to look into these papers, and I found more than 75% of papers only focus on the spatial aspect of the blue intensity method. In other words, these studies only focused on the blue intensity measured from living trees, collected from different sites and using different species. In contrast, very few studies focus on the temporal aspect of blue intensity, that is, blue intensity data measured from living trees, because as dendrochronologists, we know that dead trees or subfossils are a very important source of material that allows us to extend living tree chronologies back in time from centuries to millennia. The main reason why most studies only focused on living trees can be related to the challenges of discoloration. The best-known discoloration issue is the sapwood and hardwood color difference, as we can clearly see from here. Although some organic solvents could be used to treat samples in order to remove or reduce the contrast between sapwood and hardwood, we could often see some offset between X-ray density and blue intensity data measured from these type of samples. This discoloration issue not only occurs with dead trees, but also with living trees. And another less known issue is a stain or discoloration of subfossil materials. As we can see from the picture here, most of samples were stained with different extent of gray or blue colors. In fact, a couple of solutions were proposed in the past in order to overcome the discoloration issue for the blue intensity method. In 1999, the Shepard used extracting, bleaching, and researching technology in order to resolve the sapwood-hardwood color difference. And in 2004, Jesper proposed the delta calculation of blue intensity data by differentiating the late wood BI and early wood BI. And in 2017, Ventus used the mathematical method by combining the high-frequency signal blue intensity with the ring width data. Among these methods, Jesper's proposition is quite promising because this method is not limited by the type of discoloration, and also some low-frequency variabilities of blue intensity data could be retained. But I think the more efforts are needed in order to better understand blue intensity data measured from discolored wood could be used for climate reconstructions or not. Now I would like to introduce the major dendrochronological work conducted in our study region, the Eastern Canadian Taiga. We are here. The regional forest is dominated by black spruce, and the forest is almost intact without much of human disturbances. And the work started in the Boniface River area, led by the team of Professor Serge Bayet in early 1980s. Bayet and his team have developed several millennial ring width chronologies for this region. And in 2003, the lab member Lili Wan succeeded in developing 1,300-year MXT chronology for this region. This data, I think, is quite well known. However, the data set is not publicly available. In addition, this chronology is composed of heterogeneous sample types. Instead, a 600-year MXT chronology developed by Professor Freistring-Gruber becomes the longest available dense data for the Eastern Canada. And this data set has been repeatedly used in many large-scale temperature reconstructions. And since around 2010, my supervisor, Professor Dominique Assonneau, and his team started to use the lake subfossil materials extracted from the lakes in the Kanepisco region of central Quebec to develop several millennial ring width chronologies. And the data set has been used by several influential works such as January 2014 published in PNAS, and the two recent articles of Professor Ulf Bundgen. And the team also made efforts to develop millennial reconstructions based on stable isotopes. Like in 2015, Nollier used the 9-year smooth delta oxygen data to perform a summer temperature reconstruction. And in 2017, General T integrated the ring widths and two stable isotope chronologies to develop a millennial multi-proxy reconstruction for the Eastern Canada. In fact, their reconstruction is already very good at the low frequency domain because the correlation with calibrated temperature is around 0.90, if I'm correct, at low frequencies. But they also noticed that the high frequency variability in their reconstruction is very poorly represented. So joined with other papers, they called for the development of millennial dense data for the Eastern Canada. But considering the high cost of densitometry, we are thinking of using a kind of blue density method as a kind of alternative to the X-ray density method. For decades, Dominic and his team have collected more than 3,000 trees in the Canavesco region to develop a super well replicated millennial chronology spanning the last 2,000 years. And as we can see, the tree ring series are generally very short, shorter than 300 years, but we are still able to develop this kind of chronology because we are using the lake subfossil materials buried in lakes and lake sediments in this region. As a consequence, the subfossil materials consist of the majority of the data collection. But as I just introduced to you before, the subfossil materials will often stand with different colors. So if we want to use blue intensity to reconstruct the climate, this discoloration issue must be resolved. In the next section, I would like to present my experiments and the results. First of all, I would like to use a few slides to show you my results with the living trees, black spruce trees. And I compared 4 parameters, including lateral blue intensity, delta blue intensity, X-ray based maximum density, I would say X-ray density, and ring width data measured from 17 sites across Quebec, Labrador. To be clear, the latewood blue intensity is 30% of the darkest pixels in latewood, and the delta blue intensity data is calculated by differencing the latewood BI and earlywood blue intensity. The table shows a comparison of the 4 parameters over the last century, and we could find that the 2 blue intensity parameters are highly correlated to X-ray density data with correlations higher than 0.90. And the lateral blue intensity showed particularly high correlations with X-ray density data. I also tried to compare the tree ring chronologies against May to August temperatures, but I found that MXT data, the X-ray density, still shows the highest correlation with the temperature targets. The correlation is about 0.72, then followed by 0.71 for delta BI, 0.68 for lateral BI, and lastly only 0.48 for ring width data. I then tried to compare the temperature signal strengths of the 4 parameters according to frequencies. The results are on the left figure. We could see that lateral blue intensity, which is in blue, showed very similar signal strengths to that of X-ray density at high frequencies, but the signal strengths decreased toward the low frequencies. The most likely reason is that blue intensity is very sensitive to any colors attached to the wood surface because late wood blue intensity is a direct measurement of blue light reflectance. So any colors attached on the surface could bias the blue intensity measurements. So even for the samples without evident discoloration issue, like some color issues may also exist, for instance, due to incomplete resin extraction or whatever. And another likely reason is related to the low measurement resolution of the blue intensity method, but I would like to talk about this later. Now let's look at delta blue intensity, which is in red. We can see that its signal strength is consistently higher than that of lateral BI across the frequency spectrum. So its overall signal strength is more comparable to that of the X-ray density data. The ring width data show the weakest climate signal strength. And then I try to investigate the dependence of climate sensitivity of the 4 parameters on the sample depths. And we found that delta blue intensity and X-ray density are very similar, where the lateral blue intensity showed consistently lower climate sensitivity, temperature sensitivity according to the sample depths. So adding a lot of samples did not substantially improve the climate sensitivity in later blue intensity data to make it more comparable to data blue intensity and X-ray density. But if we look at the periods with lower sample replications, we could find that data blue intensity even showed lower temperature sensitivity compared to X-ray density. Before moving to the standing issue, I would use one more slide to show the spatial domains of the 4 parameters. And it's surprising to see that the 2 blue intensity and X-ray density data showed very similar spatial domains to that of the instrumental data in terms of the area for significant correlations. In contrast, the Ringwitz data showed much shrinked spatial domain. This suggests that the density-related parameters of living black spruce trees are very robust. So from the above analysis, we should know that data blue intensity and later blue intensity are very robust proxies for reconstructing summer temperatures, and the data blue intensity shows slightly better performance than later blue intensity. But how about the stand subfossil trees? So in the next section, I would like to present my results measured using the lake subfossil trees. First of all, I would like to record that the standing issue is so common with the lake subfossil materials collected from the Eastern Canadian taiga. In general, more than 75 of subfossils could be stand with different colors. So this discoloration has become a huge potential bias for the blue intensity-based reconstructions we will develop. And in fact, it is true, the bias can be so large if we use the later blue intensity data measured from living trees combined with stand and unstand lake subfossil trees, we will be able to develop a kind of reconstruction like this in purple. And we can see there is increasing bias back in time, in particular before 1850, when there is a high fraction of stand lake subfossil materials. And these bias can be as large as nearly 4 Celsius degrees in the reconstruction. So this suggests that we have to reduce or remove this kind of bias if we want to use blue intensity to reconstruct the climate. Although a couple of papers mention about the standing issue, very few described it in details. I think in the Eastern Canadian taiga, the standing issue has 2 basic characteristics. First of all, in most cases, only the part buried in lake sediments were stand, while the part unburied was not, even if these samples were collected from the same tree. And in addition, we find that in general, a newly cut surface was not stand, but the surface would be discolored very rapidly within about an hour after. So these 2 evidence suggest that the discoloration issue is mainly related to oxidation of some substances from the lake sediment. In fact, before my experiment, some marine chemists has already told me that the oxidation of iron might be the reason, because iron is so abundant on Earth. In order to remove the color-related biases in the blue intensity method, I compared 2 approaches. The first is chemical destanding approach, using the reducing, chelating, and bleaching reagents, and another is mathematic destanding, which I used the delta blue calculation. For the chemical destanding, I used 7 reagents, including sodium ascorbate, acetic acid, disodium EDTA, and ascorbic acid, as well as their mixtures. The figure in the bottom illustrates the treatment of a sample. 2 pieces of wood from the same sample were immersed in a kind of chemical solution. 48 or 24 hours after treatment, 1 piece was digested in order to quantify the iron concentrations remaining in the wood, while the rest piece was used for the measurement of color intensities. I also tried to sequentially extract solutions at different times for the 3 best protocols in order to describe their reaction curves. And this slide shows the destanding results. And we could find that different regions could have different destanding effects, and the 3 chemical mixtures showed best destanding results, although the colors of these wood are slightly different from that of the living tree. And the figure in the middle shows the variations of color intensities according to treatments. And we could see that red and green are more variable than blue color, but the blue intensity is still different from that of the living tree. And the figure on the right shows the iron concentrations remain in these type of samples. And we could see that the lighter samples in general have lower iron concentrations compared to the darker ones. Then I tried to regress the color intensity against iron concentration data, and I found very strong linearities for RGB color intensities in both early wood and late wood. So these results suggest that the oxidation of iron is a major cause of the staining issue. But here I would like to focus on dendroclimatology. If you are interested in the causes of the staining issue, you can refer to my article for more details. And now look at the third figure on the right, which shows the regression results for the delta color intensities. And it's surprising to see that the delta blue intensity is almost not affected by iron concentration due to insignificant regression statistic. What I did next is to compare the blue intensity chronologies measured from chemically treated samples and untreated control with the X-ray dense data, which are in red color. And I treated samples for at least 12 hours according to the reaction curves in order to make sure that reactions were all complete. And the results with little blue intensity are shown in the upper panel, and we can see that the three chemicals were not able to produce a very similar chronology to the X-ray dense data. And I was quite disappointed about it. And the correlation analysis also showed that these chronologies also only showed a high fraction of common high frequency signal, but the bias could be so large toward the low frequencies. But soon I got very surprising results with delta blue intense data, which are shown in the bottom. We can see that the delta blue intense chronologies are very, very similar to X-ray density chronology, no matter whether the data were measured from chemically treated samples or untreated control. We can see it's very similar. So, and the correlation analysis also showed that the correlations are very stable and robust across the frequency spectrum. And another very surprising result is that the chronologies measured from chemically treated samples were very similar to that of measured using the untreated control, although the colors of these samples were quite different. So these results suggest that we don't need to treat and use any treatments, so we can directly use the delta blue intense data measured from the untreated samples. As we expected, we get very surprising results for a kind of temperature reconstruction using the delta blue intensity measured from untreated samples and X-ray density. We can see that their patterns are very, very similar for the most of the time. But we should keep in mind that delta blue intensity should be more sensitive to the sample replications compared to X-ray density according to our previous analysis. So it's not surprising to observe a kind of lower statistic for the delta blue intensity than for X-ray density in our example reconstruction because we only use a couple of samples. So from the above analysis, we should know that delta blue intensity is a better proxy than little blue intensity for reconstructing summer temperatures. It's almost not affected by the discoloration issue. And in the next section, I would like to share with you some of my perspectives on the blue intensity method. The first topic is whether delta blue intensity could be valid for all the tree species. Delta blue intensity is calculated by differencing the late wood BI and early wood blue intensity. So the signals in early wood BI could also be very important. In the case of black spruce, the early wood blue intensity is only weakly correlated to late wood blue intensity, although the correlations are still statistically significant. So in this case, the early wood blue intensity mostly work as a background color, and climate signals in the late wood blue intensity could be largely retained in the delta blue intensity. In addition, the late wood blue intensity of black spruce shows some kind of negative correlations to ring width data at high frequencies. So by differencing the early wood and late wood blue intensity, some variations of ring width data could also be added to the delta blue intensity. As a consequence, the delta blue intensity parameter shows higher correlations to the ring width data compared to the lateral blue intensity and MXT data. As we can see here, the correlations as I would say like it's much higher than those expressed by the MXT and lateral blue intensity. In fact, in the paper, Jesper's paper of 2017, he had already shown that the early wood width, which is a major part of the ring width, and early wood density for many species are negatively correlated. So based on these kind of negative correlations, we can expect that by calculating the delta parameters, either the delta blue intensity or delta density, we're able to retain some ring width related climate signal in these delta parameters as well. So I believe that in many cases, the delta parameters may be valid and useful for climate reconstructions, but there are always exceptions. For instance, for the Alaskan yellow cedar, the authors were not able to present a good delta blue intensity chronology because they found that early wood BI and late wood BI values are highly correlated with a correlation higher than 0.82. So in this case, differencing the two parameters, we filter out the climate signals that will be retained in delta blue intensity data. So I would suggest to check the climate sensitivity of delta blue intensity data each time if we want to use this parameter. And my second topic is related to the bleaching protocol, because I've heard that some researchers are thinking of using bleaching protocol to overcome the discoloration issue for blue intensity. I'm personally quite conservative about it because in my experiment with the delta blue intensity, we found that bleaching protocols could alter the delta blue intensity data, I mean the raw data, compared to the other chemically treated samples or the untreated samples. So this kind of offset between the green curves and other colors have suggested that something has been already altered, but we are not clear what is it. So this result is very in a good line with the Shibard 1997 paper, which showed that the bleaching protocol could also remove the ring brightness signal related to climate. So I think the bleaching protocol should be used with caution. And my third topic is about measurement resolution, because in recent years, more and more researchers started to realize that the low measurement resolution has become a major limit for the blue intensity method, because in the paper of Jesper in 2019, he had already found that temperature sensitivity of lateral blue intensity data are generally lower than those in the parameters measured using higher resolution systems such as X-ray density or anatomic density. And his recent paper showed very similar results. And in a recent paper at about 2021, they have found that the X-ray density might also be limited to some extent by the low measurement resolution, because they found that too low the measurement resolution would result in imprecise MXT measurements. And as in some cases, the cooling peak related to the large volcanic eruptions could also be lagged due to the low measurement resolution. So we are clear that the measurement resolution is very important for both blue intensity and X-ray densitometry. So we should look for the higher resolution systems, but in fact, this type of measurement resolution is obscured by the imaging systems, for instance, the flatbed scanners we are using, because I found the actual resolution of scanned images can be much lower than the nominal resolutions. I did some tests using the resolution targets scanned under different nominal resolutions, and I found the scanner could only produce images with resolutions no higher than around 2600 by 1800 dpi in most cases. So this suggests that we will never reach the nominal resolution that we expect. So I think we should look for a higher resolution systems, but I think while waiting for the generation of new higher resolution scanners, we can still make some efforts. For instance, we can use a microtomes to smooth the surface instead of using sandpapers, because I'm pretty sure that we will get smoother surface and clearer terrain boundaries. And in this case, I think the climate signals blue intensity data could also be improved. And also we could use some optional high-resolution imaging systems, such as the one introduced by Griffin 2021. We can see that the images were very, very clear compared to those scanned using the scanner. You see, we can even see the cell wall thickness in some cases. So I think that if we can use this type of higher resolution system, we are able to overcome the low measurement resolution for the blue intensity method. So from the above analysis, we should understand that the standing issue is a great challenge for the blue intensity method, but it can be resolved by the mathematical correction of blue intensity data, that is the data blue intensity. And data blue intensity is quite promising for millennial climate reconstructions using living trees and stand lake subfossil black spruce tree. Resolution issue of the blue intensity method may be resolved by using higher resolution imaging systems. And to the last, I would still say that X-ray density is very robust. It is not affected by the standing issue and is also less affected by sample depths. So I think in the future, more dense data are also needed to serve as a baseline to assess the usefulness of blue intensity parameters. Before ending this talk, I would like to use a few slides to introduce my future works. I think in the future, we will be able to assess the validity of data blue intensity data over longer timescales, for instance, over the entire last millennium using a higher replication. We could also produce BI data from higher quality images and test for the validity of blue intensity method using more species such as broadleaf trees. In fact, I'm developing a new MXT data network for the Eastern Canadian taiga. The network is consisted of 4 sites, where the 3 sites are completely new. I performed the measurements from an unprecedented number of trees, in total composed of 1,249 trees from these 3 sites. And as a consequence, we obtained 3 well-replicated millennial ringwidth MXT chronologies plus a published chronology. So taking all of them together, we were able to reconstruct the millennial summer temperatures for the Eastern Canada. And we found that these reconstructions very highly correlated to with the temperature. The correlation is about above 0.70, and the reconstruction also showed a very wide spatial domain. So personally, I think this reconstruction or this data set is very valuable because it will not only allow us to better understand climate variability over the last 1,000 years for the Eastern North America, and also the data set could serve as a kind of baseline that allows us to better understand whether data blue intensity is a good proxy over the entire last millennium. And to the last, I do have a question to you. My question is like, can we say that blue intensity measures variations of density? In my experiments to compare the age-related trends of the different parameters, I find that X-ray density trends are very different from those of the later blue intensity and data blue intensity, in particular during the juvenile period. So do you have any ideas? And lastly, I would like to acknowledge all the co-authors of this research and funding sources that supported my research. Thank you very much. So do you have any questions?
Okay, thank you.
Okay,
yeah, thank you, Feng, for that awesome talk. It's really nice. Yeah, and it's really very nice work. I have a few questions, but maybe I don't. Let's see if someone else wants to ask anything, or if there are any comments.
I have one question to start it off, just because I've done so much we've done so much work with white spruce and Engelmann spruce in Western Canada.
Yeah.
So all our experiments for Delta blue always led to poorer performance compared to the Lakewood blue. And I would say logically, there's no reason to use Delta blue because there's no heartwood sapwood color difference for those species. So I don't know about black spruce, but I assume that doesn't really show a heartwood sapwood color change in the same way. So I wonder if this is the properties of the early wood signal and the late wood signal you were talking about, how these variables correlate with each other, because I think this is something that the community, I mean, I'm certainly, I always want to explore, why does Delta blue sometimes work and why does it sometimes not work is not fully resolved, right? And in your case, you're kind of showing that delta blue is superior to the latewood blue, or LBI, and that's not the same result we would have for white spruce. You know, so I don't know. Have you any thoughts on that?
As I introduced to you before, I think it's related to the signal strength in the early blue intensity. I mean, if the climate signal is so similar to that in the late blue intensity, I mean, by differencing the two parameters, like certainly we will have a much weaker correlations in the end. So I guess this is a major reason, but you know, for black spruce, we don't have any obvious discoloration issue. I mean, the sapwood and hardwood difference. But in our case, we still get better correlations. But also, as you can see from my correlation tables with the other parameters, the delta blue intensity shows higher correlations with green width data. You know, so
I think that's normal. I actually think that's pretty much for most species I've worked with.
Papers describing the similar stuff. So I guess this kind of improved, I say enhanced correlation might be related to the negative correlations between the green width or early wood width and the early wood density as described by Jesper, I think. It's like due to this kind of negative correlation, it's like by differencing them, like the signal, the negative signal become inverse, become positive. So it's added to delta blue intensity in some cases, but not for all, because as we know, like if the signals are the same, have the same sign and also the same strength, like we will finally get a very poor delta blue intensity record. And surprising, because it told me in the western part, you know, the Alaskan cedar, yellow cedar is also a tree species growing in the western coast. So probably it's like the environment there, like have kind of function, I don't know, on the tree growth. Like, yeah.
Maybe one thing I was thinking is, you know, even in the situation where late wood blue is kind of superior and we're kind of losing maybe something with delta blue, that might be fine when dealing with living material, but then you still have potentially this issue with, you know, when you get into the subfossil. So ultimately, you know, it's still something that needs to be dealt with somehow.
Okay.
And yeah. we can't necessarily, like, going that far back in time, we probably can't necessarily just rely on late wood blue alone to really capture those kind of time periods.
Mm-hmm. Yeah.
Anybody else? Questions, comments? Christina, Jesper. Yes.
Yes, I have a question. So I really enjoyed your talk. It was really nice, and you've done so much cool stuff. I was wondering if you have considered to transform the MXD into a delta density as a more appropriate target for your delta BI trials.
Okay. I haven't had the data. Maybe in the future I would like to try, because I think that in your paper you have said that delta proxy is better for, I don't know, the species, Scots pine or whatever. I don't remember, but it's like.
Yeah, I mean, you do something with the intraannual signal when you remove the early wood density from the MXD in the same way, or in a similar way as you do when you remove the early wood BI from the late wood BI. So I'm thinking the delta BI and the delta density would probably be much more correlated. The correlation is really high to begin with, but I'm suspecting that it will be even higher. So, okay. And also that it could have some impacts on the long-term trend as well. And you are now going into the long-term trend, so I'm thinking could be a good idea to also replicate the results with the delta density as well.
Okay, maybe it's worth to try. I would try.
Yeah, I mean,
yeah.
It doesn't cost much, I think, to
already data
parameters.
Yeah. Good.
Yeah.
Thank you for your suggestions.
Thank you.
I have just a quick question. When you showed some of the coherence results of the Lakewood blue, delta blue, and density against temperatures, I noticed that the delta blue was sort of showing a better, higher coherence with temperature than density at mid frequencies.
Yeah.
If you know what I mean. I was just wondering if you have some idea why that. So it was yeah higher than density, or
maybe. Okay, maybe I will show my slide again,
sure.
Just to check whether. Do you mean this slide?
Yeah, exactly.
Yeah.
Wait, hold on. Is it?
See the,
yeah, that's right. Mm-hmm.
In fact, the medium frequency signal is improved for the data point density. I guess, because I have to say that I found that at high frequency, the early blue density is negatively related to ring widths. That means it's a kind of medium or high frequency signal, mm-hmm. and we can see that it's truly added to data blue density. That's what I'm thinking. So it's like the variations here can be related to the signals embedded in ring width data. So that's why mostly enhanced the medium frequency or high frequency signal in data blue dense data rather than in the low frequency signal.
Mm-hmm. Yeah, I think it would also be interesting to see, as kind of Jesper suggested, with the delta density, to kind of see how that coherence would look like with the delta density.
Okay, I would like to try that. Yeah.
Anybody else? Rob?
I know this was more of a methods paper. Oh, I'm looking at myself. That's really weird. But you have some pretty epic cold responses to, I guess, 1815 and 1584. So that's more of a climate question. I mean, have you guys, is that seen in all of these sites? I mean, they stand out, don't they? It's the late 16th century, and I think it must be 1815. It showed actually put it. You had your new data, the 3 long time series from the different sites across Quebec. And I think that showed it quite nicely, actually, near the end. This one there, just at the top here. Yeah, you can see the late 16th century and 1815. I think when it was calibrated early on, that was like a 4-degree cooling for equivalent.
Yeah, that's true. That's I think it's related to volcanic eruptions. I mean, and a couple of papers also mentioned that the ice grow a lot during this period, like between 1600 and 1800. During that period in the northern Labrador Sea or wherever, it's like there was a lot of ice coverage there. So I think it's related to it reflects the cold temperature there. So but for these very cold years, I think they are related to eruptions. In particular, this one, it's directly related to tempera. And in fact, we have found a historical record of temperatures in the southern part of Quebec, and they showed that temperature decreased for around 3 or 4 degrees in the past. I think that the dense data precisely record the cooling of volcanic eruptions, and I think, yeah.
Yeah, you should publish this data quickly because with the N-Trend group are very keen on improving the northeast corner. It's just as an encouragement.
I'm working on it now. Yeah. Okay, thank you.
Great.
Anyone else? I have maybe one observation, and I forget exactly which slide it was, but when you showed sort of comparison of the reconstructions, was it based on blue data and density? I think it was really kind of clear that some of the sort of negative extremes, some of the sort of slow growth extremes that were in that reconstruction, it was really apparent that the blue data just really didn't quite weren't coming out quite as extreme, as quite as low compared to the density. So I guess that's kind of another demonstration where we see this resolution-related limitation in the blue data coming through, and even with a well-replicated data set as this, it's just still something that is a limitation and really cannot, we can't really account for it just with the scanner-based techniques. So really the high-resolution kind of approach, might be necessary to really capture these specific events.
Okay, yeah, I agree. Yeah, but also I just wonder, like, do you have any ideas why, like, the age-related trends of these parameters are so different? Like, in particular for the first 80 to 50 years, So that's why, like, I'm conservative to say that the blue density really measures the variations of density, because it's certainly not. So I don't know if some of you have any ideas about it.
I mean, all I will say is that we've noticed the same. I've never quite liked. I mean, I don't know what Jesper would think, but I've never liked the idea of transforming any of the blue parameters to a density parameter, because they don't seem to be quite the same, and because we generally detrend anyway, there's really no reason to do that transformation. So you go in with the assumption that they are measuring similar wood properties, but may not be quite like for like. And then as the new generation of methodologies come through, so we've got the quantitative wood anatomical methods, we've got Miloš's new method coming online, they're all going to be slightly different, right? And then we're getting into this nuance of statistics of, which ultimately is better. And I think it's very tricky, because I guess this might be more something for the wood anatomists to answer, rather than the users of these data, because you're looking at, it's, if you look at that plot there, the biggest differences, at least in the well-replicated aspects of these Campbell age-line curves, is in the first 10 or 15 years. And then they kind of are more similar, right? So clearly when the very, very juvenile rings are very wide, then the properties between density and, say, delta blue are very different, which probably means the properties between the early wood and the late wood blue vary as a function of tree age. But that's just my spit in the wind. But that's not my way I approach research. That's too detailed. That's for someone in a dark Swedish winter, house to work out. Who knows?
But can I just ask here? Are these exactly the same trees that you plot in these four panels?
Yeah, they are the same as I use for my paper. It's like it's an average of like more than 150 trees.
For MXD as well.
For MXD, yes.
Yeah, it's pretty.
It's like they have exactly the same measurement from the same samples, Okay.
Yep. Yeah. Jesper, is that something you've come across as well before? Like in this early like juvenile portion of the, like, for comparing density and blue?
No, I can't say that I've seen this big difference in the Pinus sylvestris that I worked with. I mean, I'm pretty surprised to see the really sharp increase in the MXD, and then just, I mean, for density or MXD, usually looks more similar to what you see in the BI on top. Like there's a sharp increase and then a gentle bump with a gentle negative slope after that. The MXD looks almost like ring width here, which is very surprising to me. Not the typical MXD regional curve.
I mean, we did I think this is definitely species dependent. I mean, certainly in our Gulf of Alaska stuff with hemlock, the delta blue generally had a relatively flat Campbell age curve, and then it was, you got a very different age curve in the early wood and the late wood, which showed a trend, right? So I think this is a question that's species specific and also maybe site specific as well, just to see how. And also, because you got these presented as Z scores, you might actually want to, for this sort of thing, you've got the noise of the low replicated older end, maybe messing around with the overall variance, so you might want to just focus, because I mean, if you're using pith offset as well, so they're not all aligned to 0, but aligned to the true first Campbell age of the, how that varies if you're using pith offset. So you might be getting a low replication bias at the low Campbell age end as well.
Yeah,
I don't know how many trees there are.
Pith offset, but yeah, it can be species specific, I would say.
Yeah.
Just one more question here.
Mm-hmm.
Have you looked at individual trees, compare them like for like, when you have the same tree and you compare the MXD against the delta BI or the LBI?
Oh, I haven't. Maybe I would like to see.
Maybe you can find some really odd examples. I mean, and see where the difference lie, because I'm guessing that there must be some of the trees must be very similar.
Okay.
That's the gut feeling, but yeah.
Okay, great.
So I guess you mean like if this is something that shows up across the board, or if it's maybe specific to a certain subgroup of samples or trees. I was just kind of thinking maybe then if it's a real effect, and at least with this particular species, it might then be interesting potentially to look at the cell wall composition somehow to kind of see whether there might be differences in this juvenile period that affect the density in terms of the cell wall structure, which then doesn't necessarily come through in, when we're looking at the color, the reflectance properties of this, and then that might be one potential. But like other than that, I also can't really think of anything else that it's interesting mystery.
Okay. Thank you.
There was a question, Jacques.
Hello, Frank. I may have a question. If you would go back to slide 33, I think. 33. Okay. I think it's 33 where you were comparing. Okay, 33. Maximum latewood density and that's 40. No, that's 42, 35. This one. Yeah, on this one, on the upper where you the A slide, around 1800, you do have like before 1800, you have a lot of variability among these, which is totally reduced after 1800, and there's a stepwise change there, and I'm wondering what are your thoughts on that? I think it's what's the difference between the wood prior to 1800 versus after 1800? I think it's mainly related to the composition of samples, because like sorry. Because since 1800, it's like we are using a kind of living tree there, like a couple of living trees, like 5 or 10, I don't remember. But in the past, we all used subfossil materials. So maybe the different materials have a kind of effect on the variance of the data. Okay. Yeah, but I also noticed that, but I think because this chronology is composed of like a couple of trees, only like 50 or 60 trees. So the replication is not very high. So in the future, I plan to compare the data using higher replications so that we have a better idea of it.
But I guess
or perhaps like I don't know if it's Milos who was suggesting to look at individual trees that would kind of go across that period and see if there's that stepwise change within individual series, or it's
yes.
Okay. Yes, it was to try that.
Yeah, I guess we're kind of seeing here that you know, that generally the subfossil portion is darker, even, you know, than the living, and
Yeah.
that's probably kind of creating this offset.
One surprising result, as I said, is like the dBi of chemically treated samples is very similar to that of untreated samples, because, you know, the colors of these samples are so different. So that means, like, at least I would say that there's not so many low frequency biases in this case, because we use the samples with completely different colors, you know, but we get a very, very similar low frequency pattern at least. But maybe it's worth to check the high frequency variability, why the variance of this data seems to be, you know, less variable. I mean, the data before 1850, like maybe a kind of stepwise change. I don't know what is that, but yeah.
Could it be related to the replication is fading back in time? Because then you get a sort of inflated variance if you have less samples.
Yeah,
Would
I
that play
guess.
in as well?
Yeah. So that's why my next step is to increase the sample replication and also extend, you know, the chronology. Maybe based on my new dense data sets, I will be able to evaluate the delta blue intensity measured for the last 1,000 years. At that time, we will have a better idea of it, I think.
I just, while we're on this, I mean, so this is a mixture of living and subfossil in that top left plot. So
Yeah.
A histogram of the death dates of the subfossil material might be interesting, because with that extreme cold event in 1816, I mean, actually, are we seeing a big die-off? And so we're just seeing a lot of subfossil material, and then we shift straight to the living material, and there's very little, because we actually have that in the ice fields in the late 17th century, where there's a huge die-off of material. And then you partly get in this white spruce there, you get this bias at the end of the subfossil samples, because the outer bit of the physical samples are darker and discolored. And you kind of have to edit that out, really, if you're not using a delta approach. And you know, that might explain it if you've got a substantial die-off around the 1815 period there, 1816.
Okay.
I mean, I guess one thing you could try if you just wanted to check like the potential effect of replication changes over time, rather than, sure, you could increase earlier replication, or otherwise you could just reduce the more recent period replication to kind of have something which is a bit more constant over time, like kind of artificially reducing it to just kind of see what that looks like. But I guess it'll just probably, I would expect the variance would be a bit more stable through time, but I don't think there would be, or I would guess there probably wouldn't be any major differences in terms of like longer term trends.
Yeah. Yes. Okay. Good.
Okay. More questions, comments, or?
We are over the hour.
Yeah, it was more or less on
time.
Can
I quickly just say to everyone, you know, as I said at the beginning, if those hadn't come in yet, that we don't yet have the next talk planned, but there are a swath of conferences coming up over in the springtime. We've got Trace and we've got Ameridendro. So if anyone actually has a conference presentation, or as a group of people who either want to use this as a sort of practice zone, or, and I'm looking more at Milos here, if people have a short talk that they want to talk to for 45 minutes, me included, then we can use the iBind seminar series, I guess, for that as well. If that, of course, it has to be blue related, but I know there's many of you out there working. I've seen abstracts for these conferences, so I know there's going to be a lot submitted. So, you know, think in that terms, even if it's a short talk, you know, we could do a couple of short talks and have a discussion. So, yeah, feel free to email me and other people in the committee, and we can arrange the next session.
Yeah, sounds good. Okay, I mean, I guess unless there are any more, anybody wants to add anything else, then I guess we're done for the day.
Wine Wednesday, everybody. Okay, I will post this video up on the iBind website if Feng's happy with that tomorrow when I'm in the university, because my internet's too slow at home to do that upload to YouTube. But I'll get it up online tomorrow. So if those who haven't seen, I'll send an email around to the whole group. So I'd like to say thank you to Feng.
Yeah, thank you, Feng.
Thank you very much.
Great talk.
Thanks very much.
And yeah, see you all at the next one, whenever that would be.
Thank you. Bye bye.
See you later, everybody.
Bye.
Thanks everyone for joining. Thank you.
Thank you. I'm sorry to be late. I will watch the video. Thank you.